Well, in the last class we have seen the basic mathematical framework with which we can generate fractals, and in the end of the last class I gave you the IFS, that means a collection of affine transformations which when iteratively applied will generate some of the well known fractals, for example the Sierpinski triangle, the Fern and stuff like that. And then obviously the question was in your mind, okay, I told you that the simple way to actually generate the fractals would be to take a collection of pixels you might start from any image, because the initial condition does not really matter, it will always converge onto that particular fractal object. So, that collection of pixels would be some number of pixels this way and some number of pixels that way, and naturally each pixel will be spanning from a particular real number to a particular real number. So, there will be these will be in effect like boxes, right. So, each pixel is actually like a box. So, start from the center of the box and see where that mapping takes you and identify which box will be filled, and again repeat the procedure starting from the center of that box. Okay. Then it will be a simple procedure by which you can generate the fractals. Some of you may feel somewhat uncomfortable to work with pixels. Many of you I found that many students feel more comfortable with working with numbers. So, in that case there are a few ways of doing it. One, you might start from just one number, means 1 point. Then if you apply, suppose there are 4 of the W's, 4 of the affine transformations available, like in the case of the Fern. If you apply each of them, how many points you will get? 4. So, in the next iterate you will get somewhere 4 points. In the next iterate you can apply the same 4 affine transformations on each of these 4 points, as a result of which you get how many points? 16, and so on and so forth. And if you do this procedure within 3 or 4 iterations, you will find that you have got the fractal object. All you need to do is to plot it. It will take at most 10 lines of command in MATLAB, very simple. But the problem is that the more you advance in terms of the iterates of this, the more will be the number of points, right. And after some time you will find that the memory of MATLAB will crash, you will not be able to go further. That is why this program, though very simple, but does not really work very effectively. After some time it will see 1 to 4, 4 to 16, 16 to, within 3-4 iterates you will find that the RAM of the computer will be swamped. One alternative way of doing it is, so this is called a deterministic algorithm, where you are deterministically applying and seeing the thing take shape. So, I have given you one algorithm in which the object changes shape, finally deform and deform and deform, and finally you will get the final fractal object. That means you will be, before your eyes you will be able to see how the action of the IFS, the iterated function system, is transforming the object, finally converging onto that object, onto the fractal object. But in this way, if you are working with points, you will not be able to see those transformations. That means how the whole object is changing and transforming and finally converging onto that, that you will not be able to see. You will be able to see that points randomly falling and finally a shape emerging out of it, right. If you progressively eliminate or delete, erase from the computer screen the earlier iterates and keep only the last one, you will more or less be able to see the final form of the fractal, but how the shape is changing, that you will not be able to see. and it is often instructive to see how the shape is changing and converging onto the final one. That is why I would propose you to go by this pixel algorithm. There is another way of doing it. The third way of doing it is, for example, in the Farn image, just recall how it was. There was one leaf here, and there was something here which resembled the whole thing, right? That is how it was. The four, okay, I'll come to that a little later. The four W's, four affine transformations actually create the four parts, but the number of points in each part generated by each part need not be the same. Means that if you start from a point and generate 4 points, from there generate 16 points, the points generated by each W will be the same in number. That means the number of points falling in this part will be equal to the sum of numbers falling in this part, and so on and so forth. That is not always desired, because it might be so that you want more number of points here than this point because of the particular shape of the object, which means that you might also assign a probability of an iterate falling here, probability of an iterate falling here, and so on and so forth. If you do that, then the algorithm would be something like this: start from a point, start from any point, and keep on applying those iterates W1 or W2 or W3 or W4 depending on their respective probabilities. Okay. So, if W2 has a twice probability than W1, then you will choose W2 with a probability double than the probability of W1. So, what will happen is that you will get a sequence which will look something like that, start from a point, then apply W1, then apply W4, then apply W3, then apply W2, then apply W1, then apply W2, then again apply W2, then apply W3. You might wonder what is generating the sequence. That is being generated this sequence, in which sequence you will be applying every time you are choosing from these 4 W's depending on their respective probabilities. In that way, the point will keep on falling, right, like this, and finally slowly you will find the figure emerging out of it. So, the earlier one is called the deterministic algorithm, and this one is called the random iteration algorithm, where the iterations are being applied randomly depending on some kind of probability assigned to it. Yes, I will come to that. So, I had given these yesterday, and there should be the one for the font. We will also need to assign the probabilities to these 4 then. That means there has to be the P, another column, right. Now, this column I will now give you. For the fund, you write down, if you want to write the random iteration algorithm, you will need to assign probabilities. This has 0.01, very low probability of this one. Explanation why I will come to a little later. This 0.85, the large, 0.07 and 0. Okay. For the Sierpinski triangle, the P's are 0.33, 0.33, and this should also be same actually, but in order to make it 1 you need to make it 0.34. They will have equal probabilities because they have 3 parts that look the same. So, essentially I have told you about 3 possible algorithms by which you can generate this. The first one is called the deterministic algorithm, where you are starting with a shape, not a point, and the shape is changing and finally converging onto the fractal. In the other, you are actually starting from a point and keeping on applying the iterates one after the other, either just in proper sequence, in which case you are not applying the probabilistic algorithm, or you are choosing from which W to apply depending on their probabilities. You can easily write the programs for that. So, before you come to the next class, at least I want one of these routines to be written. Okay, that is an assignment. One of these routines to be written, and you should be able to generate the factors. Now, let us come to the interesting point of how to generate these numbers. That is, the inverse problem is the most interesting problem. All the time I have been giving you the numbers and you have been thinking, where the hell does it get these numbers? Yes, the question is obvious, quite obvious. So, let us attack the inverse problem. The inverse problem is essentially that given a particular fractal object, how do I generate the iterated function system? The first was, given a iterated function system, how can I generate the fractal? Now, the problem is, given a fractal object, how do I generate the iterated function system? For that, the central theorem is called the Collage theorem. And the Collage theorem is essentially a corollary of the Banach's contraction mapping theorem, which I proved in the last class. The reason I went to the length of proving it was that I will need to use a part of that proof. So, let us get back there. This is what we did in the last class. We started with a distance between 2 points, 2 elements xm and xn, and we showed that that must be less than this. What is this? In the right hand side, you have got the distance between the first 2. This is the starting point, this is after the first iterate x1, the distance between them, and then in terms of the contractivity factor we got the number. Okay. And we had argued that since lambda is less than 1, therefore, this will go to 0. But now, let us start from there. If you start from there and if you now set m to be 0 and n to be infinity, what do you get? In this here, set m equal to 0, n equal to infinity. The statement immediately leads right. Lambda to the power 0 is 1. See what it says. It says that if I start from a particular any particular object, that means suppose I have got the Sierpinski triangle or something like that. So on and so forth, you have already done that. Then suppose this is my object, then I have to choose the transformations in such a way that after the first iterate you get more or less the same object. Okay. How can I do that? By writing each of the W's to make parts of the original object, right. Again, if you start from a particular given geometrical object, here it says that you choose your W's in such a way that when this whole affine transformation, whole IF is applied, you get the second one x1 that will be very close to the original one. If that is so, that means if the distance between the two objects starting point and the after the first iterate is very small, and if the transformations are contractive, then you can always say what is this fellow, x infinity is the attractor. Start from anywhere, the distance will be smaller than this number. Okay. Now, let us state this theorem in mathematical terms. It says that this is the Collage theorem. Let x d be a L is the object that we are starting with, be given, and let epsilon choose an IFS with contractivity factor so that the Hausdorff distance between the object L and the union of W n of L is less than epsilon. Okay. Where H is the then this is the theorem called the Collage theorem. See what it says. Suppose you are given a fractal object like L, say the fern, say the Sierpinski triangle, say the square be given, and now you have to choose an IFS, choose, you will do that with contractivity factor S, so that the distance between L, the original object, and the union of all these applied to the same object L is less than epsilon. Then this theorem states that ultimately the distance between Hausdorff distance between the original set and the attractor of that IFS will be smaller than this number. Now, if you can make epsilon 0, the ultimate thing will also be 0. Let us see how to apply this. Suppose I want to generate the square. Square is not a fractal, all right, but nevertheless this can generate any image. So, let us say I want to generate the square. So, this is my L. Now, I have to choose the IFS, that means the W0 W0, W1, W2 and so on and so forth in such a way that the contractivity factor is less than 1. But at the same time, after the first iterate, that means after having applied these W's on the same set L, this should be smaller than epsilon. How can you do that? Simple. You break this square up into 4 and design the affine transformation such that the first affine transformation generates this, the second one generates that, third one generates this, and the fourth one generates this. Can you do that? Pretty trivial. Say this is 0 1 0 1. From the whole one, from the whole square, how to write down the affine transformation that will generate this? Yes, 0.5 0.5 0, sorry, and EF would be 0 0 for this one. So this is when you want to generate this one, it will be the same thing shifted by 0.5. So 0.5 0 0 0.5 shifted along the x axis, right. Now you want to generate this, shifted along the y axis, this is, and let me write here so A, B, C, D, E, F, this is W4. So all these taken together will define my IFS, and then this theorem will assert that even if you start with a circle and keep on applying this, it will ultimately converge onto the square. Check it. Fine? Happy? How to generate the Sierpinski triangle? How will you generate this? Well, this will of course be further subdivided, but nevertheless the point is that you would notice that the whole, we are trying to obtain a particular transformation, affine transformation, which generates only this part from the whole. So which transformation when applied on the whole will generate only this part? The last one, same one actually. So your W1 would be 0.5 0, sorry, okay. And how will you generate this one? What we did actually, but the fourth one will not be there, and that is what makes the difference between a square and a Sierpinski triangle. This is what you had, no? You check. We had given the, this is what we had given. Now you notice, do you understand why the numbers came? Pretty simple. All that we are doing is that we are asking ourselves which transformation, when applied on the whole image, will give me a part of the image, and then we generate these parts and make a collage of it. If that collage becomes very close to the original image, then we are through. Okay, that is what we are doing. How to generate the fund? Well, let us look at the fund image first. Let us look at it from the horribly slow. No, forget it. We'll have to do some other way. Okay, look at this image of the fund. Can you see that? Okay. Here you notice that in this whole image of this fund, there is a stem. Can you see that? There is a part to the right here, there is a part to the left, and there are many of these parts, all right, but it is not difficult to see that this whole is very self similar to this part, is very self similar to the whole fractal, right. So, if we can somehow define the affine transformation that will generate this right part, this left part, this stem, and this whole thing, then we are through. Okay. Now let us come back to this screen here. We have a stem, we have something to the left part, we have something to the right part, and we have something to fine. So we need to find this. Let us tackle the first problem first. That means the whole, how can we transform in such a way, that means how can we define one affine transform that will bring the whole into this. Okay. For this, since the structure is like this, x n plus 1 y n plus 1 is equal to a b c d x n y n plus e f. The structure is like this. So you notice that if I define 2 points, which one maps to which point, then it defines 2 equations, but there are 6 unknowns, and therefore we actually need to find out 3 points and say that this point should map to this one, that point should map to this one, and third point should map to the third one. If we can define these in 3 points, then we have got a 6 equation 6 unknown case, and we can solve it, right. So now let us come back to the screen. Let me increase the size, then it will be clearer. Increase the size to gosh, it's too slow. No, too slow to be of any use. Oof. What are you looking at? No, we are looking at something else. No, leave it. It is not difficult to see that this point should map to this point. The way the fractal is oriented, there is one end here which is actually mapping to the end here. So, you get another extremity, and the third one is the starting point. The starting point must go to the starting point, all right. Oh, sorry, not this one. This is the starting point of the whole fractal, that should map to this one. So, this way, for this particular part, we are able to identify 3 points of the original full fractal object, which when affinely transformed will give the smaller one. Then we get these numbers. How? All we need to do is to put that fractal object on the paper and put a graph paper onto that, identify those points as numbers and put here. Then we can solve this, that IFS will come out. Similarly, we have to do it for this one, this one, this one, this one, and it is not difficult to see. Notice, you just get back to the fractal that you had, the IFS that I gave you last time, the IFS that I gave you last time for the fund. You notice that this is the first one. Can you identify what it means? A 0, B 0, C 0, and D only has value, which means only what y coordinate will be there, and that too the whole height will be shrunk by a factor of 0.16 and put here, right. EF 0, there is no translation. What does it do? It generates the stem. So, it generates the stem. You notice that this one is a big one because it has a large probability. The big one is which one? The big part, and these two are the two smaller ones. That is how it has been generated, and you could also generate it. All you need to do is to simply put the fund image, graph paper on top of that, identify the points, simply find which points map to which points, put into these equations, solve them, and that is how these points have been obtained. They are not God given, somebody obtained it. Clear how to do this? Okay, now this idea has been extrapolated. The idea is that, see, the fund itself is a very complicated structure, very complicated image. It is not easy to draw, it is very complicated structure, but still it is represented by only these few numbers, something like how many? 6 into 4, 24 numbers. If you add this, it will be 4 more, 28 numbers. So, 28 numbers, only this much of information is necessary in order to codify that complicated object. Can we then generalize this idea? That means, can we then codify any image in terms of such simple numbers? That is the basic idea of what is known as fractal image compression. So, that has been applied to image compression, where the basic idea is that how to obtain these numbers, which when iteratively applied will automatically generate that image. How to do that? Notice, when we talked about the Collage theorem, when we talked about the Collage theorem, did we ever really need the concept that these individual affine transforms should actually apply on the whole image? We really did not need. We could as well apply that to the part of the image to generate a part of the image. Ultimately, we have to make a collage, that is all, and the collage can also be generated from a part of the image. if we use the whole image and generate a part, then we do not need the information regarding which part it is coming from. But if we affinely transform a part to a part, then we need the information additionally that which part I am talking about. All right. But nevertheless, it is not necessary to transform the whole image. The idea is that suppose you are trying to codify my face. Yes, you can. It's actually possible. It's actually possible to find out the numbers that will be the IFS for my face, your face, and then we can start from somebody else's face and then apply that. You will see the morph. It will come to your face. It actually really happens. I mean, you can also do that coding. The point is that, of course, I cannot use the whole image of my face to generate a part, right? This part is not definitely the whole image transformed in a affine way. No, it's not. But then my left cheek is the affine transformation of my right cheek. A part of the sky is affine transformation of another part of the sky. A part of a bush can be seen as a affine transformation of another part of the bush. That means normally in any image there is a lot of affine redundancy. In any image there is a lot of affine redundancy, and that affine redundancy can be made use of to obtain the IFS. How would we do that? Suppose we have got an image, pretty large image, and it has various things in it. There would be a part of the sky, there would be trees, there would be bushes, there would be grass, there would be cows, there would be people. And then our objective then is to look for those affine redundancies. How can we do that? We will divide this image into boxes. Blocks. These are all blocks. Suppose I start from this block, then my question is that can this block be obtained from any other part of the image through an affine transformation? Okay. Of course, this, when we look for the affine transformation, it has to have a contractivity factor less than 1, and therefore what we look for is a larger block, has to be a larger block. So say we search the image and find that, okay, when this particular part is affinely transformed, it gives this particular collection of pixels. Again we come here, search the whole image to find out which part it comes from. Normally these routines are written with particular size of these blocks, say 8 pixels by 8 pixels blocks, or 16 pixels by 16 pixels block. And then if it is 8 pixel by 8 pixel block, then you are looking for the 16 by 16 pixels blocks in the whole image, from where it gives the best possible fit. Notice the theorem says about the epsilon, it does not require to be exact fit. Even if it is approximate, it is fine. It is fine. So you really want to try to get the best fit. So for each one, these are the domain blocks. For each domain block, you are looking for the rest of the image to find out which larger block, when affinely transformed, gives this block. If these are square boxes, there are only a few affine transformations that are possible. You can shrink and bring it here, you can turn it, twist it, flip it. These are the possibilities, right? So it will be only a small number of collection that can be seen from a lookup table. Which one is the best? You find out and then assign that. So for this particular block, you locate the particular source and locate that particular transformation that gives it. Enough. Go to the next one, go to the next one, go to the next one. Ultimately, you have codified the image as a collection of numbers which represent which affine transformation is to be applied and where is it to be applied. You have to search for 16 cross 16 all through the image. Yes. That will take a lot of time. That is why, yeah, that takes a lot of time, because for each one you are searching the whole image. That is why this is very computation intensive. The compression stage is very computation intensive. What people have done is that since searching for this one and searching for this one and searching for this one, they can proceed parallelly. Normally this is done using parallel processing. Okay. So initially they used to be done by parallel processing. Now parallelized chips are available, specially designed chips to do this work. There is a company called Iterated Functions, the fellow whose theorem these are. Michael Bunsley, he opened a company called Iterated Systems Incorporated. So they have made those chips that they are now available, and you can codify any image just like that. It's not difficult. Now, when you want to retrieve the image from the information that has been codified, what do you have to do? Start from any image. Start from any image whatsoever, and then again start from those bigger blocks. You know the transformation that is to be applied, you get the smaller blocks, and then you get the collage. After you have done so, you have got the first iterate. Go on applying those iterates. The theorem says that it must converge onto the image that you want, right. For example, right here in IIT Kharagpur, we had I'm sorry, this is a horribly slow machine, so it may take hours, but nevertheless, just wait to see some of the results.
So what about the color consideration?
Color will come later. So far we were talking about binary images. Let us first talk in terms of the grayscale, then we will come to color. Now, the grayscale can be treated as one depth level, right. The grayscale can be treated as a depth level. The grayscale is actually, okay, this is, make it larger. See, here is the image of you know who, Mona Lisa, and that image was codified here in IIT Kharagpur, and you start from any arbitrary image, in this case a random image, and these are the, this is after the first iteration, this is after 5 iterations, this is after 50 iterations, this is after 250 iterations, you get the image back. So this is essentially the application of the fractal image compression on the Mona Lisa image done here in IIT Kharagpur. Similarly, it can be done in all possible images. Very interesting, but it is a bit computation intensive, as I told you. You need parallel processing in order to do it in a reasonable time. Clear? Now, here you can see that this contains grayscales. Grayscale means earlier we had considered each pixel is either 0 or 1, either filled or empty, but now it will have a grayscale value assigned to it. A grayscale value assigned to it. Then the grayscale value can be imagined as either as a depth level, that means the whole problem becomes not a 2D problem but a 3D problem. That is all. No further difference really can be done. The second way of doing it is that for each pixel we have got a number. Earlier it were binary 0 and 1, now we have 64 numbers assigned to it, one of those 64 numbers. Ultimately, we have got a 8 by 8 block that we are trying to obtain by affinely transforming from a larger place, but here there are 16 by 16 points, 16 by 16 pixels, each with a grayscale value. You can apply the affine transformations, all right. When you apply the affine transformations, you get grayscale values of those obtained 8 by 8 blocks, and you can still find out the distance between the two, distance between not this distance, but the actual grayscale values, the matrix of grayscale values in this block and the one that you get by transformation. Thereby you can find out the distance. It is possible to find that. That is another way of doing it. You scan the whole thing so that you get the minimum distance. Fine. Then it will yield the same thing. Start from any arbitrary image, it will converge onto the ultimate thing. Clear? There are a few others that we had, provided this fellow is this computer is horribly slow, so it is taking a long time, but nevertheless ultimately it will come, you see that. So, can you see those images? So, it is a standard image that is used for image processing, the Lena image. Here is started from a square, and you see the transformations, and it ultimately converged onto its convergence actually. It converged onto the Lena image, starting from a white, still does the same thing, starting from a gray, and starting from a parrot, still does the same thing. So, actually you can see the transformation before your eyes.
How much time did this whole process take? Like,
No, the decompression is very fast.
no, finding out that one transformation.
Oh, that depends on the speed of the computer. Huh?
When was it done here?
What?
Was it done here in IIT?
Oh, like 4 hours? Huh. Doable time. Doable time. Well, it was done some years back when the computers were slower. I don't know how much time it will take with today's computers, but if say 4 Linux machines clustered together, that will do in very short time. But once you understand the logic, it's not difficult to write the code at all. It's very simple to write the code and do it yourself. But since the logic is elegant, the mathematics is elegant, but nevertheless this has not become the standard in image compression yet. The reason is that the discrete cosine transform, that is the standard in image compression today, that is faster when it comes to compression stage, and that is why still this is in an experimental stage. It requires really good processing power in order to do the coding part. That means the first finding the IFS, it takes a long time, but doing the reverse one, it really does not take time. So, how will you, if I give you the IFS, what will you do? Simply start from an arbitrary image, take larger blocks, and since the information that is available to will say that this particular block will transform to there, from where to where, that should be available in the code, and then which transform to apply, that should also be available in the code, so that you transform it, the next one you transform it, next one you transform it, ultimately you have got the whole image. Again apply the same logic, keep on applying the same logic. Any question? So, today with this we are coming to a close of the chapter of the fractals, and then we will go back to the study of the nonlinear dynamics. The essential thing that we have to remember, these are all fun, I should say, these are very nice things to do, but essentially these are fun, and one should do get a lot of fun out of learning. So, this is also necessary. But the relationship between what we were studying, the nonlinear dynamics and fractals, should be clear. Firstly, while we are talking about the Mandelbrot set and the Julia set, we had made some points. The point was that the Mandelbrot set essentially is a fractal in the parameter space, and the Julia set is essentially a fractal in the state space. So, when we see a fractal object, in the state space while we are studying nonlinear dynamics and chaos theory and stuff like that. Essentially, you will remember that it follows the same logic as is followed to generate a Julia set. And the Mandelbrot set idea also tells you that if a system is given by a few parameters, for example, electrical circuits are given by the inductances, capacitances, voltage sources, stuff like that, these are the parameters. The variables are the voltages across capacitor and the currents to the inductors. Now, you might also imagine a space of those parameters, okay, and there should then be, we should expect, based on this knowledge, we should expect the set of parameters for which you get a particular type of dynamical behavior to be a fractal object. Okay. A fractal object means, or therefore, the point is that we should expect fractals both in the parameter space as well as the state space. We will later see that the basins of attraction in the state space can be fractals. That means there is a attractor and there is a basin of attraction. The set of initial conditions for which the system homes onto that attractor, that set of initial conditions, that can be a fractal. And if it is fractal, there can be fractal fingers from one type of attractor getting into the basin of attraction of another type of attractor. Do you understand the kind of complexity that it can lead to? That means, if you are in a particular initial condition, there can be in the neighborhood a fractal finger of another attractor coming in, and those things do happen. And the idea about those things come from the understanding of fractals. Most importantly, when we talked about the process of generation of chaos, we talked about the horseshoe mapping, right? Smell horseshoe mapping. Imagine, so we said that in the state space of the system, there is a Smell horseshoe mapping in action. The state space is like layered. There is a continuous stretching and folding, and that could be mimicked by the Smell horseshoe mapping. Imagine that you have got the Smell horseshoe mapping. That means you take, stretch it and fold it. You then again stretch it and fold it, and stretch it and fold it, stretch it and fold it. Ultimately, if you get a cut here, what do you see on this line? Just try to think this particular point. Cantor set. Ultimately, on this line, if you slice it, then you see a Cantor set, right? And this is how all those ideas about fractals become relevant in the study of nonlinear dynamics. Why we need to understand fractals? Okay, we may not need to understand the IFS and all that, but the essential idea we do need to understand. Okay, so that is how the study of fractals becomes important. The other thing is that if a system is chaotic, we do expect a fractal object like the Cantor set to appear in its state space, and the fractals are given by fractal dimensions. Therefore, in the state space of a chaotic system, we should be able to obtain the fractal dimension to characterize that object. Yes, that is one of the ways of characterizing chaotic behavior, to obtain the fractal dimension. Okay, so that's all today.